A few of you had emailed me about some of the homework problems from homework set 15. We're actually going to go over this one in class, I think, just to make sure people are clear. But on the off chance people miss class or whatever, or sleep through class, I just wanted to quickly run through this to make sure we understand the idea of what's going on. And this is from problems 3 through 5 on your homework, which are essentially all the same, just with different vector fields. And it said, given that vector field, find the value of the line integral on the closed path. So given that, I want to find the value of the line integral on the closed path, which I've labeled right here. I do curves here, but essentially line segments from 0, 2 to 0, 0, 0, 0 to 2, 0, 2, 0 to 0, 2. And the hint that I gave was that if it's conservative, then it might be easier along a different path. And the questions I got were, well then, like, how do I show it's conservative? And once I show it's conservative, then which path do I use? And a couple of key points. I think there is some confusion between earlier in the semester when we were finding limits at a point for a multivariable function, where we had the two paths test, where we would find different paths, say path along the x-axis and the y-axis, or we use different radial lines through 0, 0. And if those limits were different, then the limit didn't exist at the point. That is not what this means. Essentially, what this means is if it's conservative, then it doesn't matter which path you choose. The fundamental theorem of line integrals says you can just take the integral at the endpoints. And in this case, if it's conservative and it's closed, then I ultimately have multiple paths here. But if my path goes from here to here, then here to here, then here to here, ultimately I'll have 3 different paths that I'll have to add up the line integrals for. But each path starts and ends at the same point, ultimately, meaning I start here and go to here, but then I go from here to here, then I go from here to here, and essentially every point gets used twice when I set up my integrals, and they all cancel out. And you should get an integral of 0, because it's conservative, it's a closed path. And again, the idea is not that you're supposed to find a new path, like we did when talking about limits of multivariable functions, but that the path doesn't matter. The fundamental theorem says every path is the same. All you have to do is plug in the endpoints of your function. But in order to use that, we have to show that it's conservative. And there are different ways to do it. For the purposes of this, we're actually going to look at the partial derivatives and make sure the curl is equal to 0. And essentially what I have to do is, I need to find the partial of q with respect to x, and I need to find the partial of p with respect to y, essentially reverse them, thinking about like the cross product from the curl. And if that curl is equal to 0, which really just means that these two are equal, then it's conservative. So here, the partial with respect to x, that's a product rule. So I get the first times the derivative of the second with respect to x would be 3y e to the 3xy plus the second e to the 3xy times the derivative of the first, which is just 3. First derivative second plus second derivative first. Okay, good. Now I do this one. I do p with respect to y. Product rule again, so it's the first derivative of the second with respect to y. So that's 3x e to the 3xy plus the second, which is e to the 3xy. 3 to the e to the 3xy times the derivative of the first with respect to y, which is just 3. And now, kind of simplifying really quickly, that becomes 9xy e to the 3xy plus 3e to the 3xy. This is 9xy e to the 3xy plus 3e to the 3xy. And now, if I actually found the curl, did the cross product and all of that, those two would be subtracted. But here, if you subtract them, you get 0, which means the curl is 0. It's a conservative vector field. Since it's a conservative vector field, it means f is equal to the gradient of some potential function. Essentially, we need to be able to find the potential function that will give me this vector field. And in class, we had gone over different ways to solve these. Some of them were like separable differential equations, and we set up the system and ultimately solved it. Some of them we had to use, say, second order homogeneous differential equations and tricks from that to solve it. In this case, it's actually somewhat easier. Now, if I'm looking for my potential function, I just need, let's see, the partial with respect to f, partial of f with respect to x would be the first component, 3y e to the 3xy, and the partial of f with respect to y would be the second component, 3x e to the 3xy. And here again, you could kind of try to do a lot of those different solving differential equations tricks that we know, but in this case, just looking at it, clearly f is going to have an e to the 3xy. It has to be there. And then just looking here, if I take the partial of this with respect to x, I get a coefficient of derivative of 3y, which is right here. If I take the derivative of this with respect to y, I get a 3x floating around, and clearly that's my potential function. Again, I'm going to skip going through all the different algebraic tricks to solve this, because that one is pretty straightforward. We already did all the tricks in class. But that tells me now, this is a conservative vector field. I found the potential function. Now what the fundamental theorem of line integrals says is that f dot dr is just equal to this function. I'm going to kind of shortcut this, evaluated along all the paths. Again, in this case, because there's corners, I have to break it up as path 1, path 2, and path 3. But again, all I would do for, say, path 1, I would just plug my starting point. Let's see, I'm starting at 0, 2, going to 0, 0. So here I would end at 0, 0 and start at 0, 2. I would just plug those into that potential function for x and y. But then I would do the same thing here. This one starts at 0, 0. So starts at 0, 0, ends at 2, 0. And then this last one right here, I'm out of room, but it starts at 2, 0 and ends at 0, 2. And I would just plug all those things in, top minus bottom, regular integration. But again, you can see just by looking at it, I mean, again, it's how, because it's conservative and closed, it's how it works. This value will cancel this value will cancel this value will cancel that value, and the whole thing will end up giving you 0. The thing I do stress, which I have stressed in class, in order to use the fundamental theorem of line integrals in this way, you have to know you have a conservative vector field, which means first you have to show it's conservative if you're not told it's conservative, and generally you won't be. Then, once you know it's conservative, you've shown it's conservative. There are different ways to show something is conservative. I just went with this one because it's straightforward and direct. Once you've shown it's conservative, then you have to find a potential function. Again, there are different ways to do it. Essentially, solve a system of differential equations like we did in class. This one was kind of shortcut, straightforward, simple, and easy. Then, all you do is plug your function, your potential function, in at the endpoints of the path. And if you end up having corners, if you will, it's not smooth, then you have to break it up along multiple paths. But if it's conservative and closed, your integral is going to be 0. If not, then you might get something else. And again, I do stress, because there were questions, understand when you say a different path might be better here, you're not actually saying a different path is better, so integrate along a different path. You're saying the path doesn't actually matter. Because it's conservative, every path is the same, so the path is irrelevant. All you care about is the endpoints of the path, which then makes the integration a whole lot easier.